Hi, welcome back. In this lecture I want to give you a brief tutorial about how to use PennyLane to create the Bell states. And I will describe what is the quantum circuit to create Bell states. This is an entangled state that have been discussed during the lecture about the entanglement. But let's give a start. In the previous lecture about the PennyLane framework, we saw the central concepts about PennyLane, that is the definition of a Q-node. The Q-node is nothing else than an assembly of a device abstraction, which can be a simulator, plus a function that is described in the quantum circuit that we want to run. So this is the core abstraction in a PennyLane. So we're going to use a Python function and define as a quantum node by using a decorator to define our quantum circuit. The quantum circuit that we want to simulate on our quantum computer simulator is the following. We have two wires, that means that we have two qubits, and when the top qubit has an AND gate as the first operation, and then we have a control operation, control node, with the target on the second qubit and the control on the first qubit. The results is something that at this point in the course we know very well, is an entangled state that is called the Bell state. So we need to do two things in PennyLane. First, define what is the device. In this case, the device is going to be a quantum computer simulator, a state vector quantum computer simulator that's called default.qubit, and then we need to define how many qubits we are going to use. In this case, wires equal to 2 is going to tell us that we have 1 qubit here or 1 qubit here, or in equivalent way we're going to have 2 wires. The second important part is the definition of the quantum circuit itself. In this case, we have the AND gate acting on the first qubit, that is a qubit number 0, and we can apply this transformation with QML, Hadamard, and then we tell what is the qubit. We apply the AND gate. After the AND gate, we have this control operation. Remember that the qubit with the control is first, so the control qubit is 0, and the target qubit is 1, and the operation is QML.C0. Then we want to return the set of amplitude. So in this case is a 2-qubit system which correspond to 4 quantum state, and this we can have the amplitude in the computational basis. So we define the device, we define the quantum circuit as a Python function, and then we can assemble as a quantum node by using a decorator at qml.qnode and then the name of the device. After we assemble, we can actually print it and display. So we can call this function from PennyLane, drawer equal to qml.draw, and we give as argument the name of the function. This will print our quantum circuit in text format that is displayed here. If we want to have an image of the quantum circuit, we can use qml draw underscore mpl and then the name of the function, and this will display figures with our quantum circuit. We want to measure and get the probabilities, either measure 0 0 1 1. So what we are doing here, we just change the output of our function. Instead of state that is going to return the amplitudes, we are calling qml.props, and then we tell which qubit we want to have the probability. Note that this is a quantum node, so in order to execute, we call the name of the function. This is going to execute the quantum circuit, and then the output is going to be included in this variable.props. After that, we can simply print the values of props, and you will see the probabilities of 0 0 is 1 over n half, and then the probability of 1 1 or state 3 is 0.5. So we achieve exactly this quantum state. We can also visualize the probability using the matplotlib capabilities. In this case, we run again the probabilities, and then we simply plotted as a histogram, as a bar here displayed on the histogram. So this is the last slides. In the next lecture, I will also provide another example on how to use PennyLane for designing and developing quantum circuits. Talk to you soon.